How to identify vibration modes from FRF. If you have ever wondered how engineers determine the vibration characteristics of structures, you are in for an interesting discussion. Understanding vibration modes is essential in fields like mechanical engineering and acoustics. Today, we will focus on how to identify vibration modes from a frequency response function. A frequency response function represents how a structure reacts to various frequencies when a force is applied. The key to identifying vibration modes lies in recognizing the natural frequencies where the structure shows resonant behavior. These frequencies are indicated by peaks in the magnitude of the frequency response function. To start, you will need to measure the frequency response function at several points on the structure. This is typically done using accelerometers or other sensors while applying a known input force. The frequency response function is a complex function that includes both magnitude and phase. Analyzing it allows you to extract important modal parameters, such as natural frequencies, damping ratios, and mode shapes. First, look for resonant frequencies by identifying peaks in the frequency response function magnitude plot. Each peak corresponds to a natural frequency of a vibration mode. These frequencies are where the structure responds most strongly to the applied force. Next, you can use the imaginary part of the frequency response function to determine mode shapes. For structures with low damping, which is usually less than 1%, the imaginary part at resonant frequencies is proportional to the modal displacement at the measurement points. By examining this component across different points, you can map out how the structure moves, defining the mode shape. Another technique is called the Quadrature Picking Method. This assumes that the modes are lightly coupled. It uses the imaginary part of the frequency response function at resonance to isolate individual mode shapes. Since the response at a modal frequency is dominated by that mode, this method helps determine the displacement pattern effectively. For more precise results, advanced modal analysis software can be used to fit mathematical models to the frequency response function data. This process extracts natural frequencies, damping ratios, and mode shapes with greater accuracy. Algorithms like least squares curve fitting or subspace methods are often employed for this purpose. Once you have the measured modal displacements, you can assign them to corresponding points on a geometric model of the structure. This visualization helps to show how different parts of the structure move relative to each other during each mode. If you do not have measurements at every point of interest, modal analysis software can interpolate mode shapes between the measured points. This creates a smooth representation of the vibration mode, enhancing your understanding of the structure's behavior. Identifying vibration modes from a frequency response function is vital in mechanical engineering. It helps diagnose structural issues, optimize designs to avoid resonant frequencies, and improve vibration isolation. This technique is widely applied in modal testing of machinery, vehicles, aerospace structures, and civil engineering components to ensure safe and efficient operation. By following these steps, you can effectively identify vibration modes from frequency response functions, gaining a clearer picture of how structures behave under various conditions.